Greg, I'll wait for you. Good? Live? Cool. Okay, hey everybody. We have an exciting lecture today because Greg and I will be giving it. And we hope you enjoy the topic. We're going to be talking about perception, which a lot of you have been asking about with respect to final projects and just general interests. And we're going to be talking about manipulation. Particularly, we're going to be talking about doing perception sort of with a domain focus on manipulation. So let's look at a little outline of what we're going to talk about. We're first going to try to get a very intuitive grasp of what does perception for manipulation kind of even feel like and look like. Then we're going to look at a brief history of what the field has done even quite a while ago. Then we're going to try to do a deep dive on one particular topic, which is rigid object pose estimation in point clouds. And then, if we have time at the end, we're going to talk about grasping. Okay, so rather than just trying to talk in the abstract about what perception and robots might look like, we thought it'd be best to just start with a bunch of visuals. So this is from the DRC in 2015, which our lab and a number of other people on campus were members of Team MIT in the competition. So this is Atlas Robot. This is, I think, during some test runs. He's holding a drill in his hand. Pat, our friend from lab, is clicking on the wall, and then Alice is going to go take the drill and drill a big hole in the wall. And in particular, you want to be looking at all of the visualization of all the different types of sensor data that we're seeing here. So all of the various colors from green to red to blue, that's LiDAR point cloud data. A lot of the other colors are, like the sort of more realistic looking colors, are from stereo data that's fused together with the depth information. And then in his hand, you can see that even though it was outside of the sensor field of view, Atlas knew that it was holding the drill, and that's what helped it make that plan. You see a little bit of motion planning there with footsteps, like Robin talked about last lecture. So this is what, at least for some robots, perception might look like. Here's another view. So this is one part of the tasks in 2015 was to drive a car and then get out of the car and walk around. And as some of you may know, maybe that moment was one of the hardest moments, especially for Team MIT. It's just a very challenging task to do that. It's just rich with contact. It's hard to do sensing. It's a very challenging thing to do. And again, in this visualization, you can see a lot of different types of sensor data. One that there isn't really much of a visualization for other than the effect of it is obviously all the joints have encoders, and so that's how Alice can know what configuration all of its arms are in. You can see a little bit more of footstep planning like Robin talked about last time. And Alice gets out of the car, walks around, and goes and grabs a bunch more stuff to complete the tasks. Let's look at another type of perception. So this is from the final year of the Amazon Picking Challenge. So this is just last year, 2017. And this is from the team that won, an Australian team, ACRV. And this is a little video that I grabbed from them of what part of their system looked like. So in the top left corner in particular, you can see the first-person view of a camera which is on their end effector. And they actually had a pretty nifty custom-designed end effector, which on one side had a gripper and on the other side had suction. And so they can alternate between those two. And in particular, that the sensor that's mounted on the actual end effector, that's the main one that they used for perception in this task. You can see it right there. And this is a little bit of kind of what perception for them meant. So they did a lot of semantic segmentation of different objects that they saw in the bins that they were trying to pick out of. And over on the right, we'll come back to that picture later, but that's a colorized point cloud of one of those objects, that monkey. And there's a lot of little aspects about that point cloud that I think are useful to note. We'll come back to that later. So as we've already seen a little bit of, but and some of you may know all about these, but just to make sure we're all on the same level, everybody should know what RGB sensing means. So come 2010, there was a big moment in the field, both for robotics and computer vision and related fields, that Microsoft came out with their Kinect sensor. And there had been depth sensors before, for a long time before, but this was the first commercially available at a reasonable price. So I think it was only about $100. And I think there's some fun fact that computer vision community loves, which is that I think it outsold like the iPod or the iPad in its first 100 days, something like that. It was an amazing selling product. And I think it's useful to keep in mind, where did robotics, from my view, get this gift? And it was really from the gaming community. So you see the Kinect, which is underneath the TV there. And for those of you that aren't familiar with the Kinect, although I'm sure many of you are, this was the sort of application that was in mind. So, it's been around for a while now. But getting away from just holding hand controllers, and you can actually interact with the game just through depth sensing and a variety of computer vision techniques. So that's been a huge gift to the robotics community, and there's been a host of other RGB sensors since. Intel they actually have a whole slew of them. This is just one of them, the SR300. There's been many others, although I wish there was even more. To get everybody a really good sense of really what this data looks like, this is next to Greg's desk. And this is I believe this is an SR300 mounted next to Greg's desk looking at a variety of objects. And here is a very good look at all the data that comes out of an RGB sensor. So some of you may be very familiar, so we're all on the same page. In the top left, that's the depth image. And in that depth image, the pixels that are darker are closer to the camera. The ones that are lighter are farther away. In the bottom left, we have just a standard like you would get from a webcam RGB camera. And then in the right, together with a little bit of 3D geometry, you can fuse those two pieces of information if you have nice calibration, and you can get that representation on the right, which is a colorized point cloud, and we saw a bunch of those earlier. So Greg's going to move some things around in this view, and useful to look at what we do get and what we don't get. So one thing is, as you could see a lot before as he moved the camera around, and as you see with his arm and the plates in front, like occlusions are real, and occlusions turn out to be a very fundamental and challenging part of a lot of computer vision, especially for robotics. Also, Greg is holding a clear glass right now. A lot of depth sensors don't work on clear things. I think there are ways that the field will figure out how to deal with those, but for now, we just don't touch clear things. Another thing too, which you can't quite notice that well in this particular shot, but maybe around the edges of the plates, a lot of depth sensing doesn't work very well at very high incidence angles to the camera. And those are all very fundamental challenges in terms of the quality of the data that comes out. Okay, another very basic thing that I want to make sure we're all on the same page with is when we talk about perception, we're doing it's a little bit different than some of the way of thinking about the world and a very control-focused way of thinking about the world. So we have a quadrotor here. This is from Skydio, which was founded by a bunch of MIT people, and we like them. It's a very impressive robot. And this quadrotor is flying around, and we've studied a lot of control techniques so far in this class that are very good at stabilizing that quadrotor to a fixed position in space, or helping that quadrotor design how it wants to move through space in some optimal way through trajectory optimization and things like that. And the controllers that we've thought about in that context, what do they take in? They take in what we would call the state of the robot. And so for this particular one, some of you may know that for any aerial vehicle that doesn't have some other sort of actuation like a joint, that's going to be a 12 degree of freedom state. And I like to just write it out just to keep it all in mind, but it's XYZ position, the orientation of the world, which is another 3 variables, and then the first time derivatives of those. So we think about the state of this robot as being 12 off. How about the state of the world? What do we think is the state of the world for this robot? Let's take a guess.
I'm going to take a guess that in their application, they really come with the runner and the robot and not much else. Everything else is good.
Okay, great point. There's sort of 2013, 2014, 2015, there was a lot of products which cared about the state of the quadrotor, the 12-dot state of the quadrotor, which you would get through something like GPS. And they also cared about the human, and then you could also have the human wear like a wrist tracker, and you could also have the state of them. And that is true, but a key feature that this robot focuses on is obstacle avoidance and autonomous mapping and planning in the world. So it really cares a lot about the trees and everything else in the world. So how might we represent those? Let's take a look at what they do, which is a very standard way to think about this in the field. This is particularly impressive, though. So this is a voxel map of the world over time. It's very good. So if we think about that state, how big is that state? So this would be my rough guess based on that video. I'd say they probably have about a 50 meter by 50 meter in X and Y, but you don't need that in Z, and they're not showing voxels in Z that high, so maybe 20 meters. And then it looks like the voxels are about 20 centimeters in size. So rough math, that's about 6.25 million binary variables, which are just occupied or not. And you need a few other continuous variables to have that sort of relative to your robot, but that's it.
Okay, based on the video, it looks like they were only including some subset of the voxels that would be in the relevant space for navigation.
So the ones that weren't there, those were the non-occupied ones in the visualization.
Okay. So
yeah.
Considering the area away from the trees non-occupied, they're still competing the occupancy grid?
Yes.
Even though they don't have information about it, because presumably their sensors are blocked by the trees.
So I think I knew what you meant, but then I'm not sure. We can go back and watch the video again, if I can get it to play again.
Because you can drop out a lot just by considering which part of the grid you care about.
So anywhere where you see a box, it's saying that's occupied. Anywhere where you don't see a box, it's saying it's not occupied. The colors they look cool, but they're just a visualization of how far away something is from the robot's field of view. Okay? So one simple observation is that for most different types of tasks for one particular robot, we kind of think of that as having a canonical state. It changes a little bit based on what the robot's doing, but for the most part, a robot has a state. And if it's a robot arm, it might be 7 degrees of freedom. If it's a quadrotor, it's going to be 12. But the state of the world is very task specific. So they actually do care about the human state as well. But for this one, this is a quadrotor. So all it really cares about is just not hitting anything. So it just wants to know where things are and things aren't. And that is a sufficient state of the world. Let's take a look at a different robot. What is this robot's state? Well, unless you're modeling things like the state of the springs and things like that, a pretty good state of this robot, Waymo autonomous car, would just be its X, especially on a flat surface, would just be X, Y, and the orientation, and then the time derivatives of those. But how about the state of the world? So for an autonomous car, it actually is going to care about velocities of dynamic objects in the scene. The previous robot we saw doesn't need to care about those as much because it can stop much faster. This is a different representation of state. And for this one, you see how there's bounding boxes around the different objects, and they're classifying them. So you might have a variable that classifies them, and then you're going to try to estimate each of their states, or their velocities and their positions. So that's another way of thinking about state of the world. How about for manipulation? The state of the robot, I think, for manipulation is relatively straightforward. Usually we have a robot arm, and we know very well what its state is. And I think in the other ones, especially quadrotors, it's very hard to do state estimation. I also want to say, when we say that state estimation for a quadrotor has 12 degrees of freedom, but the world has 6.25 million binary variables, that it's not to say that the ratio of how many things there are makes perception of the world that much harder. I'm not myself an expert in doing depth perception in a quadrotor context, but I've worked with a lot of folks that are. And it turns out if you have really good pose estimates, then estimating the depth perception of the world is much easier. And just really nailing the state is a very valuable thing to do and very hard to do very well. I think it's safe to say that the field in manipulation has not converged on what is the right state of the world. There's a lot of different ideas out there, and it very much varies based on, even just within manipulation, what you're trying to do. So if you go to any MIT professors that are involved with manipulation, and you ask them, what is the canonical task in manipulation? You'll either get like a smile and like a good question, or maybe a variety of answers. But I think it's very hard even just to define what the right task is in manipulation. To point out some other things about this world that we might care about, this is a fusion of a bunch of depth data that we took up in our lab. So this is like a drill and a helping hands and a little soft robot sitting on the table. If we think about this mesh, it's got almost 1 million vertices and 1.5 million faces. But I want to point out something about rigid objects, which is that if we know some sort of geometry of the rigid object, and in a lot of manufacturing contexts, for example, like you have a CAD model because you made the thing, then there's this very rich geometrical representation of this object if it's perfectly rigid. It's got a couple 100,000 vertices, a bunch more faces. But in terms of its state in the world, as long as it stays rigid, that is perfectly defined just by its 6-stop pose. And in fact, often if you're like sitting on a table or something like that, then you're sitting in some manifold in 6-stop space. Okay, so hopefully through a bunch of videos, and that's going to continue to be a trend of this lecture, that gives you a little sense of what we mean when we're talking about perception for manipulation. Let's look at what people have been doing for a long time. I think in robotics we don't often appreciate what people did even very long ago. So for this little section of the talk, I do want to give credit where it's due. I'm leaning heavily on a great talk by Stephen Seitz from 2011 called The History of 3D Vision, and highly recommended. So like many good things in technology that get invented, it turns out that a PhD thesis by Lawrence Roberts, who later went on to be one of the founding fathers of ARPANET, which is, first iteration of the internet. He's often referred to as the father of computer vision. I took that from Stephen Seitz's talk. And if you pull up his PhD thesis, you'll see this figure. And this was a big achievement at the time. So this is what we call block world. And in the top left corner, this is an image that was given to a program that Lawrence Roberts wrote. And through some image gradient operator, which was like one of these first image gradient operators, then in the top right, that's where he's applying that operator. In the bottom left, that's where he's extracting the lines of that image. And the achievement here, the main achievement, is that he can take that and then render that from a different view. And back in 1963, that was a lot of things to do, and this is all in one MIT thesis, kind of like what's his name invented information theory in his master's thesis. So this is a big achievement in 1963. And as Stephen Seitz says in his talk, this particular piece of work inspired basically like an entire decade of research on the block world problem. And another great piece of work that Stephen Seitz points to is, and it's very funny, it's hard to find good documentation on this thing. It's like, it wasn't a paper, it was like a demo, but apparently it was very influential. But so these are, this is Patrick Winston, MIT professor, Freuder, and Berthold Horn, also MIT professor. This is back in 1970, and they kind of had like everything together. They had a robot arm, they had a hand, they were going and grabbing stuff, and in a very block world sense, this was all based on trying to find lines from images. There's a bunch of assumptions, of course, that you need to make about shapes of blocks and then sitting on planes and things like that. But then it would find these blocks, it would go stack them in different ways, this whole planning system to stack them. I mean, you see a lot of papers like now that look very similar to these types of figures. One thing that came out of this was that they did find that it was very hard for them to reliably find lines and edges, and that, apparently this piece of work spurred a whole bunch of research, and we got to be really good at detecting lines and edges. And I think the main, a main result from that area is the canny edge detector, which is, if you know computer vision history, is very well known, and that works very well. And that, for example, in a block world, I think would nail that task, even with that era computer vision techniques. So this is another one, another MIT professor doing a bunch of things back in the day. This is from Tomás Lozano Perez. And like many systems of robotics from that series of decades, they all had great names. They would, like, if you know about the shaky robot or this is the handy robot, they all had like these kind of dog but not dog sounding names. So this is another robot that did basically everything. So they didn't have Kinect sensors, but they had depth maps. And they would use the canny edge detector and the depth map, and they would fit these blocks. And then if you look at the list of things they would do on the left, they would locate the object, choose a grasp, do all these different things, re-grasp it, put it where it needs to go. Like they did everything. And actually, I think it's not in this paper, but I think it's in the next one. One problem that they solved, just like trivially, like, oh, obviously this is no problem, is that if you know all the graphs of an object and you know all the stable resting modes of the object, it's just trivial graph search to figure out how to grab it, then reorient, and then put it back down, and that whole series of maneuvers. This is a figure from the paper just showing the sequence of plans that Handy would do. So that was just 3 quick papers, a very sparse subset, but that was a brief historical look. And I'm going to hand it over to Greg now.
Sup, can you hear me? Coming through okay?
Yep.
All right, so Pete has hopefully set up a great motivation with a huge series of videos. Showing robotics videos is pretty much the best thing in the world. It's so much fun. Robotics videos are awesome. I'm going to try to ground things a little bit in what is kind of a classical way for perception lectures, but hopefully tie in some of the subjects that Pete's been talking about of doing particularly rigid object pose estimation in point cloud data. But I'm going to try to frame it in a kind of optimization sort of way to make it make sense in the context of this course and give you a little bit of math that you can hold on to kind of give you an entryway into this enormous field of perception for robots for manipulation. So the subject I'm interested in delving into is this rigid object pose estimation, particularly with point cloud data. And a core assumption of all that, as Pete's already started to mention, is that we're going to stick to only thinking about rigid objects. And what I mean by a rigid object is that we're going to have some object. I'm generally going to draw things planar because that's so much easier. That has a fixed shape that we know a priori. We can expand this down the road to try to estimate object shape online or add deformations, but everything is much easier when we know it a priori. And this object has some pose in space, which is a translation, which is 3 real numbers, and a rotation. Rotations are kind of hard to say what exactly they live in. Formally, they live in a special orthogonal group of matrices that satisfies some specific conditions. But we're generally going to, at least for what I'm going to talk about, treat them as 3x3 matrices. So they live in real numbers, 3x3 matrices. And to satisfy living in SO3, that means that R transpose R is going to be the identity matrix. That means that every row and column of R is unit. Every row and column of R is unit length. Its inner product with itself is 1. That's on the diagonal, and R is a orthonormal basis. So in terms of thinking about R as a transformation matrix that you'd apply on a vector, what that means is that R will not scale things, will not skew things. It will only rotate things. And there's an additional constraint that we have to add just for formality, that the determinant of R has to be positive 1. That's not actually forced to happen with this individual constraint. If the determinant was negative 1, this rotation would also mirror whatever objects you're rotating, which would be generally a bad thing. So with this restriction on objects, that our objects must be, we must know their shape ahead of time, and that shape must not change, and the only degrees of freedom they have is just moving around in the world. What situations is that actually good for, or what situations is that bad for? Anyone have any thoughts or situations you're interested in that this might not work for, or this might work well for? Yep.
I mean, I guess if it's skewed, then, like basically, in any case where you're not looking at it head on.
So it does. We can handle skewing of objects. That really is more a measurement, more a feature of what kind of way you're representing your sensor data coming in. If your sensor data, your sensor model includes some kind of perspective transformation that does, that does any of those skewings or distortion, we can still capture that. But if the object itself, like physically deforms, any case where you're operating on deformable objects, I know a group that's currently working on doing automation for the factory line assembly of Chipotle burritos. That is a horrible situation for this. This does not work at all. But there is a huge world of situations where this does work, which is pretty much any situation where you're operating on all the man-made tools that we like to use, factory line items. A lot of the stuff that we use is really pretty rigid because deformable stuff is harder to manufacture, harder to deal with, harder to pack, harder to interact with and make robust. We really have a lot of fixed objects in the world. So this is really a pretty okay assumption and has gotten robotics really, really far. So Pete has already demonstrated what exactly this RGBD point cloud data we're looking at is. One more thing I forgot about objects. This is critical. How do we want to represent the objects, particularly the object shape? We're going to need to decide how we're going to do that. There are many different ways of representing object shape. Pete put up a beautiful mesh of this really high-resolution scan of a drill. And that way of representing it is that usually you're going to store a bunch of vertices of the object and a list of faces that are groups of those vertices where the plane that connects all those vertices is solid. Really standard computer graphics way of storing everything. That's a great way to represent objects and works really well, but I'm actually going to stick to a even simpler representation because the notation is a lot easier. I'm going to say that we're going to, for any object that we have, sample a huge number of points on its surface and take that set of points as our object representation. So in particular, each of those points are going to be indexed through this talk MJ, the complete set of points being a big matrix M. Okay, so with that out of the way, how do we actually want to do any kind of perception? So I'm going to think about things in a maximum likelihood sort of a way. This is really familiar, like treating things kind of with probabilistic views and ultimately probably invoking Bayes' rule and then doing some operations based on what that tells you is really common in state estimation all over the place. Many of you have likely seen it or possibly know a lot more than I do about it. So I'll do my best. But the way of starting that always starts with, we're given our measurement, in this case a point cloud measurement Z, and in the case of point clouds, this is going to be a list of point observations of the world, Zi. So each of these are three vectors. Over in the context of our object over here, they'd be some points out in space would be point observations Zi. And we'd like to find some pose of the object, or we want to find a configuration. I'm going to abbreviate X, which is the configuration of our robot. In this case, X is a pair of a rotation and a translation, satisfying those constraints over there. And the way that we're going to frame this is we want to find the X that is the maximum likelihood given that we've observed this particular sensor observation. That makes sense as a sensible thing to do. That's really just translating into the language of writing out a likelihood exactly what question we want to answer.
Are you guaranteed you get all of the places you guys belong to the object?
No. In general, no. We don't have the guarantee that every point that we observe is going to belong to the object. For what I'm going to talk about here, I'm going to make that assumption and then relax it down the road. Choosing which points as outliers is super hard. We'll find that we already have to make a choice of what part of the object every point corresponds to. Making the additional choice of whether it's an outlier or not is an additional choice on top of that one. Anything else? Okay, so this is if you kind of squint at it and look at it, something like, or if you think of evaluating, I'm given a set of points, and I'd like to figure out what pose generated that set of points. Like you'd like to find just the maximum likelihood pose. That requires, written this way, doing this kind of inverse graphics thing, where you have a pipeline where it's pretty easy to think about, given an object, how I generate points on its surface. But given points on its surface, regenerating the object is not super straightforward. So I'd like to flip this around, and I'm going to justify that with Bayes' rule. So just invoking Bayes' rule, I can flip each of these around. And as kind of brief hand-wavy justification, particularly because this comes back up later, this term doesn't depend on x at all, so I'm going to ignore it for the rest of time. And this term, it would require having some kind of prior belief about what poses of the object are more or less likely to happen. And there are lots of places you could get that kind of information. You could go look at where this object has tended to appear. You could, if you had prior information about where the object used to be, you could try to do some update through time, which I will do later. But for now, I'm going to assume a uniform prior and also get rid of that. So that's the hand-wavy justification for, I would really like to deal with this easier forward measurement model. So this is, I'm given some object pose, it's a lot easier to think about what points are going to be generated from that, or how likely points are to be generated in space based on a given pose. Okay, so let's think about what we want that measurement model to look like. So again, we're given, sorry Pete, I keep moving around. We have an object in space somewhere at some given pose. We have say an individual scene point out in space. And our general intuition should say something like, this scene point is more likely to exist the closer it is to the surface of this object. So it should be very likely to be spawned here, and decreasingly likely the farther it is away from the object. And we can formalize that into the notion that we'd like the probability of a given scene point, given a pose of the object, to fall off in, say, a kind of Gaussian-like way with a distance function, which measures the distance between this point and the closest point on this object surface, which will be a function of what that point is and also the pose of the object. And in our classic Gaussian distribution-like way, we add some notion of how uncertain or how noisy our sensor is. So we get to bring in some measurement of how noisy the sensor is, which is great, and we scale with how far we are from the object, which is great. So this is something that we can build up.
Is it negative or positive?
Oh, yeah, sorry. Where was that coming from? Yes. Thanks. Okay, so this is a reasonable model for an individual point, and we're going to make an additional assumption immediately that all the points are independent. I was thinking about that a bit when writing this, and that's kind of dangerous. It doesn't really make sense that all the points in a picture should be independent from each other. And throughout the literature, people acknowledge this sometimes and kind of acknowledge that their estimates of the uncertainty in this are generally underestimated because they're making this assumption. They assume that really parallel observations of the same object are really two independent observations of the object, when that's not really true. You have large-scale noise in your image sensors. But for driving this algorithm, it works pretty okay. It's just a thing to really be aware of when you're using this, and especially when you're trying to estimate like the certainty of things that are coming out of ICP. Coming out of anything built on this. So to combine all of these together, we're going to write the full Remember, we're still maximizing over our poses of, now we'll just take the product of all of these individual observations. So that form works, and kind of viewing through the lens of this class, you could feasibly just directly optimize over this if you define the distance function, which we could do down the road. But this form kind of sucks a lot because it's a product of a bunch of already kind of nasty terms, so all your optimizers are going to hate this. So immediately we're just going to take the negative log of both sides to get this down into a more familiar, more natural sum form. I'm doing the negative kind of because it makes stuff work out nicer, and we turn into a minimum, which we're more used to. So taking the negative log of both of this statement, we wind up with minimizing over x, a sum over terms. We get the log of product turns into sum of logs. Log of e just goes away, and negative gets rid of that extra negative sign. So sum of distance functions, and the noise I'm going to bring just all the way out, so we don't really have to worry about it. It's now just a scalar factor.
What do people do if they're not going to take the assumption that all the observations are parallel? Like, I can see like making illusions where they depend on each other do not do that.
I don't really know how people tackle it when they're trying to push through things in this more careful probabilistic framework. I don't have as much experience with that. I'm thinking in particular, like when I say that, like at the end of all of this, we're going to wind up with an optimization that we can estimate the stability or uncertainty of its final solution. And in general, at least the papers I've seen for that say, we know that this is probably going to be an underestimate, so we just add a constant factor to it to try to assuage that. And they're estimating that across time, and no one really ever uses that uncertainty anyway, so it works out. It's not great. I totally agree with you. But the problem's already so huge that dealing with it's really hard. Yeah, Pete?
And also, often, I don't know if in this specific context, but often the answer, if you don't like types of probability assumptions that are made, Monte Carlo in the limit of infinite sampling is always correct. So you could, sample a ton of different distributions, or a ton of different poses of an object, and then figure out which points are more or less likely. That always works. It's just very expensive.
Right. You bring up a great implicit topic related to that is the problem of sensor modeling in the first place. People are really good at simulating RGB scenes because video games and movies, but people aren't really great at simulating really good depth images yet. It's a thing that people have worked on and people are actively working on now, but including things like spatially correlated error in your simulations of depth sensors is kind of a new thing. And it's a thing I think that's still being explored. So what ramifications that'll have on our estimators, we really have to finish simulating it first. But it's an excellent question. Okay, so the last step, so this is looking like an optimization if we define the distance function that might be of a form that we might like, despairing that we're actually optimizing over rotations, which is a little nasty. So let's define the distance function more formally. And this is where some of the nastiness of dealing with point cloud data in particular starts to rear its head. So our distance function, we really want to be given some point out in space, go find the closest point on our model to it. Our model is represented as a set of model points. So our distance function then is going to be a minimum over all model points. So a minimum over, I'm using J to index model points here, and we also have to take into account that we have an object that's at some given rotation and translation. So we're going to transform our scene point into the model frame and then take the difference with a given model point. Sorry, that's in shadow a little bit, but is that readable? And does that make sense? So this is just really exhaustive search over all of the model points. Check the distance in model frame between the scene point, which we've just transformed to model frame here, and that given model point. And we'll use probably Euclidean distance here. So putting that all together, substituting that into here, we wind up with something that's really not too great. I'm going to drop the 1 over sigma for the moment. So it's a, sorry. I really want to write out with both mins because I like emphasizing how weird this looks. Min of x, sum over min of j inside of the sum. So for every scene point, I need to go find its closest point on the model of this point distance. That's workable, but also really nasty. But that, if you solve that, will give you a maximum likelihood estimate given all of the assumptions that we've made of where this object is in this point cloud. And that's the thing that we could start to think about tackling. I'm going to make one final transformation to it to get it into a form that doesn't have nested minimizations and kind of expose the combinatorial form of this under the hood. And I'm going to write this down and then try to explain it because the notation gets a little bit dense trying to encode all of this together. So we're going to transform this into, this is writing exactly the same thing. It means the same thing. A minimum over an x, you can substitute out r and t. Minimize over a rotation, a translation, and a matrix of correspondence decision variables. This is a matrix where every row is a set of binary variables where exactly one of them is 1, where you're using these binary variables to select which model point corresponds. So the vertical axis is indexed by the number of scene points. The horizontal axis is indexed by the number of model points. And this enters in this way, that now we get to sum over model points. We're taking a similar norm, rzi plus t. And then we're using this correspondence matrix to select which model point we're going to be taking the distance to. And formally, the constraints that this has to have are that R has to be what we expect it to be. R has to be a rotation matrix. C is a matrix of only binary values. So that's size z times size m. And the rows of C sum to 1. So that's sum over j of a given row of C for all scene points. So that's dense, but the whole trick here, this is exactly the same as this statement, except I've now substituted this inner minimization with this selection term that I have here, where this is missing exactly one thing here. The ith row of C multiplies the whole set of model points, such that if C satisfies these constraints, this turns out to be the given model point that you've selected by choosing which of the model points is set to 1. That okay? Does that sit okay with people?
Oh, it just seems like the one above is way easier to write heuristics for, whereas the one on the bottom is...
Right, and that's a great observation and is important. This will wind up to be a more natural form for the way that kind of this problem gets classically solved, though really you can translate between the two anyway. But this form exposes exactly what I think this problem is under the hood. So just staring at this, kind of bear with the notational messiness. What form of optimization is this? The idea is you could be as naive or conservative as you want.
So as it's currently written, I think it has a square root in there. So
Yeah, this will inevitably, well, if you expand these things out, at least you'll have squared terms. So this winds up being at least a quadratic objective in terms. Your decision variables come in here, here, and here, and this whole thing winds up being kind of a sum of squared terms. So your objective comes out to be quadratic. So you are in that realm. You're certainly not a linear program. But your constraints are where a lot of your interesting behavior come in. R being a rotation matrix. Remember the two constraints that this turns into. R transpose R is the identity matrix, which is has a bunch of bilinear terms in it. The determinant of R is 1, which also has a bunch of bilinear terms in it. And then even nastier, C is a bunch of binary variables. And do I need to ask if the set of binary variables is convex? That's bad. That's a nasty set of constraints, but a really powerful one at the same hand. Do you guys remember Robin talking about mixed integer programming last week? Did you ever mention it?
yes.
So this is exactly a mixed integer program because it has these binary variables. The term mixed integer or mixed binary kind of get convoluted. Usually people use binary variables. Russ is on a quest for problems where people actually use integer variables, so if you have one, let him know. He'll be very happy. So this is a mixed integer nonlinear program because of this nonlinear constraint. If you make some approximations of this is the only other nonlinear constraint. You wind up with a mixed integer quadratic program, which you can actually solve to global optimality pretty efficiently, which makes this form really nice because if you write out everything this way and you make that rotation matrix approximation, you can actually find the optimal pose estimates of objects in point clouds. Even if you add outliers, even if you start adding a couple of other tweaks multiple objects at once, you can handle those things. But the trade-off is that you're solving a mixed integer program, so it doesn't scale that well. It is still, exponential time worst case, possibly worse. It works, and it's a really cool theoretical result, and I really like it, but it's probably not the easiest way to solve all this. Okay, so that form is what I really want people to hold in their head when they're thinking about this problem, that you're really making a choice of what point every scene point corresponds to simultaneously. So for every scene point, you have to make a choice. And all those choices interact with each other to produce whatever optimal pose estimate you have. And that's a really hard underlying problem. So how do people actually tackle this in the real world? So looking at this form may help you, but I'm not actually sure which one this statement is going to be clearer in. But to start with the intuition of this, if I give you the rotation and translation, how easy is it to find the correspondences?
Just like a binary search of the distance or something.
Yeah, right. If I tell you exactly where this object is, then for every scene point, just go check all the model points. That's going to be like quadratic complexity, worst case, and if you store your points a little bit more intelligently, a little bit more carefully or efficiently, then you can do better. So if you have the pose, then finding the correspondences is really easy. What about the other case? What if I give you the correspondences? How easy is it to find the rotation and translation? And for that I think this form may be helpful. The two forms collapse to the same thing after that. Yeah, so maybe not. So fixing correspondences, you wind up with, you lose the really nasty integer constraint. These suddenly get fixed. So the only constraint you have is optimize that quadratic objective over the set of rotation matrices. And that feels almost tractable. And I wish I could go into all the details, but I'm probably already going to make force Pete to not do the second half. So that is something you can do in closed form, and I think that's kind of mind-blowing. That if you tell me for a set of points, I have some object, I don't know where it is in space, but I have a set of observations, and you've told me exactly where on the object each of these are going to lie. Solving that problem is something you can do in closed form. It relies on some of the magic of kind of orthogonality of solutions to the singular value decomposition, but it's something you can do. And if you want to read more about that, I would reference you to, this winds up being something you can translate into Waba's problem, I think it is. Am I corrupting that? Waba's problem? But that's really cool. So if you fix either of those two decision variables, you get to get the other one for free, which leads you immediately to a algorithm for solving this using local search by alternating between those two things. I should have said earlier, when the safest problem class to call anything is a nonlinear program, because you're usually right. And a very safe way to try to solve every nonlinear program is with some kind of local search method. So your impulse, especially nowadays, would be look at that and say gradient descent. And that almost works, except that gradient descent on integer variables is really hard. By really hard, I mean I don't really know what it means. So you wind up doing the bigger brother of gradient descent, which is this kind of expectation maximization or alternation style algorithm. So for people familiar with ICP, I'm sorry to have belabored this, but I hope it's given you some insight into kind of the underpinnings of a very popular algorithm, dates back to at least the 90s.
92.
Almost certainly, like Tomas would say that he came up with it before that or something. So this is the iterative closest point algorithm. Commonly abbreviated ICP, and the idea is really fix. So you're given some initial pose of the object. You use that to so you fix R and T, and you find C, and then alternate by fixing the correspondences using you fix your correspondences and you find a new R and T that is hopefully better than the previous one you had. So that does seem like kind of a stretch that would really converge to anything useful, but it proves to be really pretty great at least if you start in the neighborhood of a reasonable solution, this works pretty well. So shown here is a point cloud. This is like a side view on a table. You can see the base of a big arm up at the top. And shown in these fluorescent colors are two really simple models of two objects I'd like to fit in this scene. A can of compressed air and the tabletop. And this video demonstrates that if you just spawn these in this pose, it's close to the right pose, but it's really not anywhere near it. It'll do its best to fit these to that point cloud data in exactly the way that you'd kind of intuitively like it to. It shoves them inside of the point cloud data as best it can. And I like this video because it shows both that it does what you expect it to. It slams the two together. But it isn't great, and it's not great for a couple of reasons. One is that the object model just isn't right. This box is approximately the right height of that can, but doesn't have the tapering at the top. So the optimal solution isn't going to have perfect overlap. And even if you were at the optimal solution, which I'm not totally convinced this is, did you notice when this started out that then when it slammed in, it actually slammed in. So if you had dots on your object here, the box was up here and didn't really perfectly overlap your point cloud very well. And just thinking through what each of the iterations of ICP is going to do for this. In this case, I have a bunch of points of my model. Each of the scene points corresponds to the closest point on the model. So in that case, that goes here, that goes probably there, that goes there, that goes there. There's that, and the only points really pulling this box downwards in the direction it's supposed to go are these few points down at the bottom, and they're fighting everything else to pull this box down. There are algorithmic changes you can make to ICP to alleviate this. You could change your distance function, for example, to calculate the point-to-plane distance. If you know the normal of every point on your model, then you allow the model to wander around in its plane without actually having any penalty. And lots of other ways that you can do this, rejecting outliers, whatever. But ICP really is local search at the end of the day, and it does struggle with things like this. But the things you can do with it if you start out in the right neighborhood are kind of incredible. So this is that same arm doing a manipulation task on all of the stuff in the boxes here. And every mesh except for the arm is being tracked just from this point cloud data. So you can see that, yeah, it struggles with flat surfaces a lot. But as you shove that box around, as you move anything around, you can know where it is in space. So this gives you a really powerful tool to build up these completely autonomous manipulation systems. And starting out, just looking into the world and being like, how do I even begin to parameterize this? That's kind of exciting. So here's that was a very early video of one of the first times I tried to run this stuff. Here's a little bit more mature version of this. This is completely autonomous. It's scripted. It's not making any clever decision making about how the world works, but it's going to a bunch of motion targets relative to the position of the box. So if you move anything around, this will still work. And it's entirely powered by ultimately ICP under the hood. And it'll go through the whole process. You can be distracted by it. So I did tell you how to fit objects. I didn't tell you how to track them, but I think your best guess is probably right. This algorithm you run until convergence, and if you just never stop it, you wind up with tracking. That's maybe the simplest way of saying it. But let me revisit just one detail here to make that not quite such a silly, simple statement. In the tracking world, we're going to actually want to rewrite this term here. So I guess stare at that and I'm going to erase it. Sorry. I'm going to rewrite this now with some implication that we're actually going to do this over time. So we're given both a measurement, and we're also given wherever we were at the previous time step. So we are tracking across time now. We're going to make a Markov assumption that our state really only depends on the previous state, and that everything before that doesn't matter at all. And that works pretty well for this kind of tracking. And we'd like to find our new configuration at the current time point. And maybe for completion, this is our observation at the current time point. So saying the same thing again, this is going to be maximizing the maximum likelihood estimate of our current state given our observation and our previous state. Going through Bayes' rule again for really the same reasons. I'm I'm dropping xk minus 1 here because really our current observation should only depend on our current state. There's not really any memory in the sensor, so I feel justified in that. This is the term that we had dropped earlier that was our prior over states. This is xk minus 1. And that's the term that is really interesting. And then, of course, our normalization stuff in the denominator, which is just becoming an increasingly weird term that we're going to ignore because it doesn't have anything to do with xk. So this is the term that I kind of want to draw attention to. We already went through deriving why it's okay to just optimize independently across all of the points with respect to this measurement model. But whereas just looking at the prior distribution over individual states was kind of a scary looking thing, now we're looking at, that is going to factor in here. This could be factored into our prior distribution over states and also really a dynamics model. This is exactly our robot dynamics. It's how our state evolves from our previous state to our current state. And I'm going to skip over the rest of it. Really, this starts factoring in when you do your log. This becomes another term you get to add into your optimization, so you can start to have it starts to look like a regularization over your fitting based on wherever you expected the robot to move to. But I think I'm kind of low on time, so I promise there is more to this than just running ICP as fast as possible. This opens a whole world of putting in understanding of the robot dynamics into your tracking. And at the risk of spouting what it might be an opinion, very few people really make a lot of use out of this in the manipulation world. Manipulation really is not, people are very scared to be very dynamic about it, with a few exceptions of for example, a lot of the stuff Alberto did during his PhD at CMU and does now, with Matt Mason at CMU. He has a long history of doing really awesome dynamic manipulation stuff. But I think this term is kind of critically underused, and really a lot of the benefits of stuff from this class can be translated and put into the world of perception, really closing the loop here, using really the combined efforts of what you have observed about the world and what you understand about how the world is supposed to work. And this is really where they got to come together. Okay, enough soapboxing. So putting that all together into something that wasn't just a offhand experiment years ago. This was probably also years ago, but it wasn't an offhand experiment. B, can I ask how I can step through this video?
Good question.
The general intuition of ICP is super useful. It's that you want to align, really anything that requires aligning 2 point clouds is a good fit for it. So one of the other cases that many of you are likely very familiar with is the problem of scene reconstruction. If you're, just as Pete is showing, when you have a quadcopter flying through a forest, you'd like to build up a model of what that forest looks like. And you can use this proves to be a really useful tool to use in the middle of that process. So what that would look like kind of in abstract is that I have some partially constructed model of an object, but I have some kind of uncertainty about that. I'm still in the process of building it up. So I could have only had partial views of the object. Awesome. Or I could have uncertainty about the exact geometry. And it's too distracting. Let's do that. I think we solved the core problem of stepping through this, though.
We did.
Oh, we're back where we started.
It's my goal.
Okay, here we go.
Mine is here.
So this is looking right now. It'll get to better views in a minute. But this is a pair of the robot is looking down with a camera at its hands, and it is estimating the state of every part of its hands and that object that it's interacting with, using essentially at the core this ICP as a tracking algorithm running continuously with a good understanding in the way that I was just mentioning of additional information about what the dynamics of these objects should be, particularly that there's going to be non-penetration, which gives it really good estimation in this manipulation case. And the estimates that it gets are really, really beautiful. The level of precision they get out of this tracking, even with what really looks like fairly noisy data, by integrating it over time and having a good understanding of how the world works, how non-penetration with the collision geometry they have here works, and by averaging across time, they wind up with really, really good estimates and can do really, really fine manipulation tasks. I was super inspired by this work when I first saw it. It's kind of why I went down this road. So I'm super happy to share it with you. Okay, as mentioned there, if you have a partial model of an object, I think this video does it better than Chalk ever will, you can use the same idea of fitting new point clouds to your partially constructed model to build up your understanding of the model. So if you have any partial view and you get a new view of some new part of it, you can register the two together by really just minimizing the distance between their collective points and obtain that way new information about your model, which you can fuse in using the details of any of these fusion methods. And for you might see this in scan matching from planar LiDAR as you're driving your cars through the basement, or looking at planar scenes here. And this is also one of the core tools used in putting together a lot of modern SLAM techniques, SLAM systems.
In order to do that, do you have to know how much overlap you expect?
Exactly, something I kind of skipped over. Let's let this video get where we need it to first. Something I kind of skipped over is dealing with the problems of outliers and how to handle outliers. So what I had written down originally was a maximum likelihood estimate given that there were no outliers. But if you start adding outliers, you need to start deciding, well, how many outliers are there? Am I going to search over the number of outliers there might be and find like the best explanation? You have to start adding some kind of penalty for making things outliers or reward for having inliers. The general way that people do that is you start all of those searches and alignments in approximately the right place, and usually you reject the top n%, like you only accept the top 30 or 40% of correspondences as inliers, the correspondences that are the closest ones, or you reject all the ones that are further than some fixed distance away. And everyone has their own favorite heuristic. So these are videos that you may have experienced before, or this might be your first time. If so, enjoy them, they're awesome. This is exactly that technique of incrementally building up maps by registering each image, each depth image to the previous model you've built up, but done extremely rapidly across time, super efficiently. And what you get out of it is beautiful high-resolution maps of huge amounts of space. And for free, because you've co-registered all of these point clouds, you also get the pose of the camera as it moved through that space. This is early-ish work on solving the simultaneous localization and mapping problem that's really ubiquitous in robotics now. And then if you go even farther with that, you can start to add articulations to this model. I didn't go into that too much, and the brief justification of it is that in your original optimization, in that final optimization that you come down to that looks like min over robot configuration of sum across all of your observations, your distance function, which is a function of your configuration and the scene point. This doesn't have to be just a 6-DOF pose. You can define and evaluate distance functions and optimize over them, even if this could be a 6-DOF pose, so rotation and translation. It could be a robot configuration. For example, all the angles of a robot arm, or a deformable object that's been modeled with a bunch of individual rigid bodies or with some kind of finite element model. The possibilities are really endless there. And so the gist of this work is that they do exactly that. They've added articulations to the model they're reconstructing. So they have an understanding of what their model mesh is, and they simultaneously optimize the reconstruction of the mesh by adding in new data. They add new data by co-registering their new scan with their current deformed mesh. And then they alternate that with optimizing new deformations of their mesh. So they have a canonical model, which really is whatever they've seen first, and then they register a new scan. So they have a current understanding of how warped it might be. They register their new scan to that warped model, add that data back to the canonical model by doing the reverse transform, and repeat that forever. And the results are awesome. And this is only getting better with time. There are variants of this that are super awesome, work at even higher resolution, work faster, work for larger volumes. This stuff's super cool. And to emphasize, at the heart of all this is, or a super useful piece of all this is this ICV algorithm. So I'm going to throw it back to Pete. Hopefully that was a fun foray into some of the underpinnings of this foundational tool. You'll see it everywhere once you start looking for it. So I think back to Pete with some grasping stuff.
So we talked earlier about it's very hard to define what is the task of manipulation. And I think the answer is that there's many different ones. But one task that has been done a lot is grasping. In particular, the general task of put a bunch of stuff in front of the robot, go pick something. I don't care what it is, just go pick something. That task has been done a lot, and there's been a lot of impressive results in that area. So let's think about some of the techniques that Greg just talked about and the type of sensor data that now, if you weren't familiar with before, you know we have now. And let's think about how we grasp objects. So there's been a lot of work over the years in if you have one of these mesh models for an object, then doing grasps on that. And it's actually a very hard problem to come up with what is the optimal grasp. That is actually quite hard. Turns out that there's a lot of grasps that could be good, but computing optimal ones is quite hard. On the left is a paper from our lab that uses some of the tools we talked about in the class applied to that problem. But aside from optimizing over the best grasp, in order to do that, what you want to have is you want to have some sense of what makes a grasp good. And without going into the details there, just at a very high level, in the class we've talked a lot about contact modeling. You've seen Russ and Robin and Chuan draw on the board friction cones. And if we have some object and then we're grasping it, then we're thinking about grasping the object, we're thinking about the contacts of our fingers with the object, and we're thinking about the friction cones that we're modeling, and we want to think about how robust is that grasp, how good is that grasp. There's a lot of different ways to do it. One good way to think about it is if you're grasping in a certain way, how well can you sort of deflect forces and wrenches that are applied to the object that you're holding, right? So how well can you hold on to it is the gist of it. So this is a paper that has a certain metric that they define very carefully that a lot of people use. So if you have a known mesh model, you can use one of these analytic grasp metrics to decide how good your grasp is. You can try to do various types of synthesis. But it does assume a known mesh model. And I flashed a video at you before, a pretty influential challenge that has happened over the past few years. It's done now, but I think there was a challenge in 2015, 2016, 2017, and that was the Amazon picking challenge. I think they called it the Robotics challenge in the last year. And there's a great history in robotics, as many of you know, with challenges, a lot of them from DARPA, sort of spawning a lot of good research in the field. Back with the DARPA Grand Challenge, which was one of the first autonomous car big research efforts in the mid-2000s, and even well before that. So the Amazon picking challenge, if you look at all the teams, this is from a review paper of what all the teams did. If you look at this column, a lot of them assumed that they had these known mesh models. I was given in the first year of the challenge that you could have mesh models for the objects you were trying to grab. How about if we don't have mesh models for the object? We can, as we're showing in the top right, you can get very rich if you're careful about calibration and other things. You can get very rich geometric representations of the objects that are in front of you, even if you've never seen them before. And it turns out that actually in a lot of cases you can just apply these same grasp metrics and just try to go grab something in the geometry in front of you, and that turns out to work pretty well in a variety of cases. But there are challenges. So in that mesh fusion in the top right, there's a lot of different views that are all combined into one. But this is a figure from the winning team at the Amazon Picking Challenge in the last year, the ACRV team. And you see that this is this monkey, it's a little plush monkey, and you can't see any of the sides of it, right? Because you have your depth sensor just on top. And the first time you think about that problem, you might say, oh, well, that doesn't seem that big of a problem. But actually, that's kind of like the only reason why we need, I think, the next set of work that I'm going to tell you about. But it is very fundamental and very important, I think. So if things are very cluttered, you can't see all of it, or if you just only have one view, you can't see the whole object that you're trying to grasp. So a couple different ways to think about trying to grasp unknown objects that you've never seen before and you only have a partial point cloud. It turns out that there's a few different groups that have worked a lot on this type of technique in the past couple of years. But if you do two steps, one, you simulate partial point clouds on a whole bunch of known mesh models. So you go to this thing called ShapeNet, and they've got thousands and thousands of mesh models like this. Okay? And what you do, which is kind of shown here, is you go and you take your sensor and you take the object and you, in like a 3D video game type simulator, you render a bunch of point clouds or depth images from a bunch of different views. And then you try to see from that view, we use these analytic grasp measures to decide how good that grasp is. So what this turns into, so again, one, you simulate all these partial point clouds, and then two is you try to learn the probability of grasp success given only partial point clouds. It's a little weird of a crop of that image. I don't know where that came from. But what that is just showing us, too bad it's sort of weirdly cropped there. What they're defining as S to be is the success of a certain control input. So we've seen a lot of U's and X's on the board in this class. U is a control input. X is the state of that robot and mesh system. The success of that being a successful grasp would be a 1, or that event would be either a success or not, so a 1 or a 0. That next line is missing. But if I can remember off the top of my head, that's just simply saying that what you want to estimate, since you don't know that, is you want to estimate some measure of the quality of a grasp, which would be the expectation of that S, given not U and X, but given U and Y, where Y is the actual measurement that you have, because you don't have the full state. And then what you're trying to find is some optimal theta, where theta is all the parameters of some big deep neural network that can try to model this task. So you're trying to do argmin overall parameters of the expectation of, this is a loss function which they use, cross entropy loss of the actual S and your estimate of the expectation of S. So just to give you a look at the type of results that you can get with this technique. This is Jeff Mahler's work at Berkeley. Here's a bunch of shape models. You already saw that it can grab a bunch of different things. This is a depth sensor simulating a partial point cloud, and then you go and pick up a whole bunch of different type of objects. This is a very comparable piece of work. These both came out about the same time, very similar approaches. I think this is a great video. They show a very cluttered just pile just coming out of a box. And a great visualization in the bottom left corner showing different grasps that they are evaluating how good they are based on this trained model that they have, and then going and trying them out. And with these types of techniques, you can get well above 95% success rate on grasping fully unknown objects. It's a very popular piece of work the past couple of years. So if we look back at the Amazon Picking Challenge, in 2015, they had all these known mesh models. In 2017, Amazon said, we don't have mesh models of all of our millions of objects, so you can't have mesh models. I think they might have also said that in 2016. I forget the timing, but definitely not in 2017. And if you look at the teams that won, actually a handful of teams did very well. The winning team, again, was this Australian team, ACRV. Team MIT and Princeton also did very well. I think they won one of the tasks, the stowing task. There's a couple other teams that also were in the mix of doing very well. But if you look at what they actually did, like many of these challenges in robotics over the years, there's a lot of convergence to a very similar solution. And so there was a lot of some mix of smart heuristics on computing what we think would be good grasps based on the RGB and depth data, and then a lot of brute force human labeling of images, so thousands and thousands of images, people sitting there and saying, okay, I think that little part looks like it would be good for a section grasp, and that little part looks like it would be good for a grasping grasp. And some data set of thousands of images that have been labeled by humans, and using that to, you can kind of see these. This is for the MIT Princeton. A lot of it turns out that suction also just works really well in practice. So humans labeling in a bin where are nice places to suction, and then having that just evaluate on time with the RGB and depth data, where are good places to section in the image. ACRV, a little bit different approach, but very comparable. The train segmentation that they have was on segmenting the objects, but then the actual way that they would take segmentation and then decide what to do with the objects was more in the heuristic realm. So they would have really good segmentation, and then they had this series of heuristics where they would say, if they can calculate good surface normals, surface normals turns out to be a really good heuristic for is my suction grass going to work. So if they find good surface normals, they do that. If they can't get good surface normals, then they try to get some centroid of some point cloud. But then it turns out that not all objects even have good point cloud data, as we talked about before. So then they would just take their segmentation if they didn't have good data in those two ways, and they would just compute the RGB centroid of that object from the segmentation mask. So these types of tricks, these is very comparable. A lot of different teams use this type of approach, and this is how teams won the Amazon Picking Challenge 2017. So let me look at the time. I've got one more slide, but hopefully you feel like we've gotten a sense of all these different topics. We did not cover a lot of things, so I just wanted to flash some of them at you. We did not talk at all. We talked a lot about vision and point clouds and RGB, but we didn't talk at all about tactile sensing. And I both think that, my view is that the manipulation community has a lot to do even without tactile sensing. Like there's a whole bunch more that robots could be doing even just with vision. Also, though, I think we have a lot of really amazing sensing modalities that have come on in the last few years, and I think if you think about how you and I do manipulation of things, tactile sensing is very valuable, so I think we'll see a lot more there. We also, and this goes for other things that we talk about in the class too, we haven't talked at all about, which I think is very relevant, especially manipulation, but like, what even am I doing? You know, like how do I plan some very long horizon sequence of tasks? That's just not something we talk about, but I do think it is closely related to perception and long-term planning. So this is work from Leslie and Tomas's group from RSS a year or so ago. Just the figures just showing you, like, if you have all these things on a table and you want to put them in a certain way, how do you even go about doing that type of a task? And another thing we did not talk about today, but we will talk about reinforcement learning later in the semester, but there's also definitely a lot of work in this area of manipulation on deep reinforcement learning. So basically trying to get robots to manipulate like we've been very successful at getting computers to play AlphaGo, where you sort of take images directly and try to have a neural network predict what you should be doing. A lot of work in that area. So that is it for today's lecture. I just wanted to flash up a few things related to logistics for the class. Project update is due 1 week from yesterday. We do have office hours on Monday and Tuesday next week. You can come by and chat about your projects. And then we will release assignment 5 when that project update is due. Any questions?
In the unknown object sort of model, how do you know what's an object and what's not?
Great question. How do you know what is an object and what is not? Often the reality is in any robotics demo that you see, there's a lot of curation of that environment, or even if it looks very general, there's been a lot of particular prior knowledge that's been given to that robot about what it should be looking for. And I think that is definitely something that, as we talked about how the field hasn't converged on what is the state of the world for robotics, for manipulation, I don't think there's a great answer for that yet. Thank you.